Good evening. We are going into our next session on our chapter waves. And today we're going to start a session with the superposition principle. So now if you are at a concert or let's say a musical program, many different instruments will be playing at the same time. So as these waves, the sound waves travel through the medium, each particle of the medium is receiving energy from different waves, that is, different instruments. So each of these particles will be displaced from their mean position depending on the energy it receives from each of these waves. The superposition principle states that the net displacement of a particle of this medium at any point is going to be the algebraic sum of the displacements produced by the individual waves. For example, if let's say one wave produces, we have a particle at this point here, we have a particle which is receiving energy from one wave which displaces it through a displacement y1, and at the same time the next wave, the second wave that is traveling through the medium acting on this particle simultaneously produces another displacement y2. Then the net displacement of the particle y will be the algebraic sum of the displacements produced by the individual waves. So if let's say this particle is acted upon by two waves simultaneously and one displaces it through plus 2 from the mean position and the other causes a displacement of minus 1, then the net displacement of this particle will be plus 1, which is the algebraic sum of plus 2 and minus 1 will be the net displacement. This is what superposition principle states. Now, based on this superposition principle, we are going to look at a phenomenon which we called as the interference of waves. So here we are going to consider two waves which travel along the, let's say, the same direction, positive x-axis. So we may represent the first wave, y, which is the instantaneous displacement of the particle at a given time, is going to be equal to a sine kx minus omega t. As you know, this expression represents a wave which is traveling along the positive x-axis. X minus tells you the velocity is positive. Now we have a second wave traveling simultaneously through the medium acting on this particle, which is given by a sine kx minus omega t plus phi. Now you see these two waves have the same amplitude. They both are traveling along the positive x-axis. They have the same wave number, same frequency, but they differ in the phase difference, that is initial phase. Here the initial phase of this wave is 0. Here we have a phase of phi. That means, for example, suppose you take a particle at the origin. So x is 0 and at time t equal to 0. Here in this case the initial phase is 0. So if you put x equal to 0, t equal to 0 and phi equal to 0, we have sine 0, which is the displacement produced at time t equal to 0 on a particle at the origin is going to be 0. That means it is going to be at the main position. Now for the second one, at the same time, that is the particle is at the origin at time t equal to 0. Let's say this is pi by 2. So then we have sine, this is 0, but sine pi by 2 gives you 1. So the displacement of the particle is maximum, that is at A. So this is what you mean by the two waves maintaining a phase difference of pi by 2. So now superposition principle says, so this is just an example. So superposition principle says the net displacement produced is going to be y1 plus y2, which means I can take the A common outside, sine kx minus omega t plus sine kx minus omega t plus phi. Now here I can use this as A and this as B and use the identity sine A plus sine B equal to 2 sine A plus B by 2 cos A minus B by 2. Using this identity, I am going to expand this and write y equal to this 2 into A, I am going to take it outside, 2A bracket, sine A plus B is sine A plus B by 2 cos A minus B by 2, which means we have sine. Adding these two, we have 2 kx minus 2 omega t plus phi by 2, and cos, we have subtraction. So we have simply minus phi by 2. This term is not dependent on time. So it's a constant, meaning if phi was, let's say, pi by 2, then phi by 2 would be pi by 4, 45. So it is not dependent on time, because cos 45 will then have only one value, that is 1 by root 2. So it is not dependent on time, and therefore cos phi by 2 is a constant. And cos of minus theta, you know, is cos theta. So I'm going to write together this 2a cos phi by 2 into sine 2kx, this will be kx minus omega t plus phi by 2. Now you will see that this is the resultant wave or the resultant displacement. This resultant wave is also a traveling wave which is traveling along the positive x-axis, having the same wave number and velocity frequency as the individual waves, but having a phase difference of phi by 2 with respect to the first one. The important thing here is the amplitude of this wave, which is 2a cos phi by 2, which tells us that the amplitude actually depends on this phi, the phase difference. So that means you can have constructive interference where the amplitude is maximum. So for maximum amplitude, I hope you've understood that this is the amplitude of the wave, because when we have a function a sine kx minus omega t plus phi, which represents a traveling wave, this is what you call as the amplitude. Comparing this with this, you see this is the amplitude of the resultant wave. So this resultant wave can have maximum amplitude, which is equal to 2a when this cos phi by 2 is going to be equal to 1, which means when phi equal to 0, you will have cos 0 as 1, and therefore you have the maximum amplitude at if the waves maintain a phase difference of 0, which means if you have one wave traveling through the medium in this manner, the second one also is in phase. There is no phase difference between the two. There may be a difference in the amplitude. In our case, we have the same amplitude. So the two waves will have the same amplitude in our case. They are in phase. They do not maintain any phase difference. Both the waves are starting at the origin, you see, at t equal to 0 and x equal to 0. The initial phase is 0. So they do not maintain a phase difference. In this case, the amplitude of the wave will be equal to 2a, which is the sum of the amplitudes of the individual waves. That means if one wave produces, let's say, plus 2, the other one also produces a amplitude of plus 2, then the amplitude of the resultant wave will be double that this will be 2a. That is plus 2 will be 4. On the other hand, if you can also have destructive interference where the two waves completely null each other, which means if you have, let's say, minimum amplitude which is 0, can happen when phi equal to pi, which means cos phi by 2. So the amplitude is 2a cos phi by 2, which is pi by 2, which is going to be 0 because cos 90 is 0. So if you have two waves that maintain a phase difference of 180 pi, let's see how they look. You have one wave like this. The next one maintaining a phase difference of pi. Pi would mean this is 0 and this is pi here. So your next wave starts like this. So we have the other wave which starts like this. And if they have the same amplitude, let's say this is plus a and this is minus a, you will see that the algebraic sum would give you net displacement. The amplitude will be 0. So we have, or let's say imagine this is a string. So we have two progressive waves traveling along the string in the positive x-axis. The initial, remember our first wave was y1 is equal to a sine kx minus omega t. The second one is a sine kx minus omega t, maintaining a phase difference of pi would mean this is the first wave and this is the second wave which is having a phase difference of pi. In this case, we have these two waves traveling along the string, but they undergo destructive interference, and therefore there will be no motion of the particles on the string, and this is what we see as destructive interference, and this is what we see as constructive interference. So here we have just discussed this phenomenon of constructive and destructive interference as two waves travel along the medium in the same direction, maintaining a phase difference phi. We now go on to discuss another phenomenon which we call as the standing waves or the stationary waves. Standing waves or stationary waves are produced when two waves travel along the medium in opposite directions. So in that case, we need to take the first wave y1 as a sine kx minus omega t, and y2 equal to a sine kx plus omega t, showing us that this is traveling along the positive x-axis, but this is traveling along the negative x-axis. For simplicity, we have taken that they maintain a phase difference 0. The initial phase in both cases is 0. So that means both the waves have initial phase 0. They are having no phase difference. They have the same wave number, same frequency and same amplitude. So that things will be simpler for you to derive. Now superposition principle says y equal to y1 plus y2. And like before, we have a common outside, sine kx minus omega t plus sine kx plus omega t. And using the identity as before, sine a plus b equal to 2 sine a plus b by 2 cos a minus b by 2. I'm going to use this as a and this as b. And you will see this is going to be equal to 2a, and in bracket we have sine a plus b by 2. So this will get cancelled. We have 2 kx by 2 cos, and this will get cancelled, and we have omega t, 2 omega t by 2, or I may write this as 2 sine kx and this as cos omega t, or I may write this as 2a sine kx bracket cos omega t. Now this clearly does not represent a traveling wave or a progressive wave, because if we need to represent a traveling wave or a progressive wave, it should be of the form a sine kx minus omega t, x minus or x plus or z plus or zy, something like that, showing you that this wave is propagating energy along the, energy along the positive x-axis. Now you will see that this is clearly not of that form, and therefore this is not propagating energy. This is simply an oscillating term like we did in oscillations, a cos omega t. So this just represents an oscillating wave, and such a wave is what you call as a stationary wave or a standing wave, where the wave does not propagate energy along the medium but simply oscillates. This is the oscillating term, oscillates with the frequency omega. So for this wave, this displacement, this wave, this happens to be the amplitude, and you can see that the amplitude depends on the position of the particle from the origin, x. Let us see what happens here. Let us look at the amplitude is of this resultant wave, that is the standing wave or the stationary wave, is 2a sine kx, clearly indicating that the amplitude depends on the position of the particle from the origin. So you can have positions of zero displacement, zero amplitude, when 2a sine kx is equal to 0. These positions where the amplitude reduces to 0 is what you call as the node. They are stationary. So the condition is 2a sine kx must be 0, or it shows that sine kx must be equal to 0, which means kx can take values. Sine you need this 0. So sine 0 is 0. Then sine 180 is 0. Sine 2 pi is again 0. 3 pi and so on. Or k, as you know, is 2 pi by lambda. X should be equal to n pi, where n can take any value and so on. So if I cancel this, I may write x is equal to n lambda by 2, showing that from the origin 0 lambda by 2, 1 lambda by 2, 2 lambda by 2, 3 lambda by 2 are all positions of nodes where the particles do not oscillate, simply remain in their stationary in their positions. That is, if I take these positions as 0, then this is, let's say this is lambda by 4, this is lambda by 2, this is 3 lambda by 4, and then we have a lambda, and then we have 5 lambda by 4 and so on. Okay. So if I now substitute n equal to 0, this is a position of node where the amplitude is 0, never oscillating. Then if I substitute 1 here, we have lambda by 2, again a position of node. If I substitute 2 here, that's again a node. So we have 0, lambda by 2, lambda and so on. 3 lambda by 2 are all nodes. Every integral multiple of lambda by 2 are positions of nodes, stationary, which means these particles never oscillate. They remain stationary in their positions, which means they do not receive energy at all from the previous particle. So that is why we call it as a standing wave, because if these particles never move, they simply remain stationary, it simply means they are not receiving energy and the energy is not being propagated along the x-axis. Whereas in a traveling wave, you know, the first particle receives energy, starts oscillating with an amplitude A, imparts that energy to the neighboring particle, that particle also starts oscillating with an amplitude A, and all particles of the medium will at some time start oscillating with the same amplitude, showing us that the energy is being transferred along the medium. That is what you call as a progressive wave or a traveling wave, represented by the equation A sin kx minus omega t plus phi. But this is a standing wave, and that is clearly shown because we have positions of the medium where particles do not receive energy, do not oscillate. We can also have positions where we have the maximum amplitude, which is given by the maximum value that sin kx, 2a sin kx can take is 2a sin kx. Because of this can be plus or minus 2a. When this is plus or minus 1 is the maximum value. Or sin kx can be plus or minus 1, or kx can be taking values. When does it take 1? Sin pi by 2, 3 pi by 2, that is 270 is minus 1, 5 pi by 2, 7 pi by 2 and so on. Or k is 2 pi by lambda x can be odd multiples of pi by 2. So 2n minus 1, this is an even number, minus 1 gives you an odd number, pi by 2. Or I can cancel this and write x is equal to 2n minus 1 lambda by 4, and these will give you positions of antinodes where n can take values 0, 1, 2 and so on. So now if it takes, let's say, start with 1. If it takes 1, then we have 2n minus 1, that is 1 lambda by 4. So we have this as a position of antinode, where the particle is oscillating with maximum amplitude, which is plus or minus 2a. So this will be plus or minus 2a. We also have the next one, 2. If I put 2 here, that is 4 minus 1 will be 3 lambda by 4, which is again oscillating with maximum amplitude. If I put 3 here, that is 6, that is 5 lambda by 4, also we have maximum amplitude. So you see, you have a stationary wave or a standing wave where each particle, depending on its position from the origin, will have a given amplitude. The particles are the antinodes here, 3 lambda by 4, 5 lambda by 4, are all oscillating with maximum amplitude plus or minus 2a. The particles at the node are stationary. If you take another particle which is here, you see it has its own amplitude depending on the position of the particle from the origin. So, which means energy transfer does not happen here, because each particle, if it were to receive energy from its previous particle, it would have transferred the energy equally, and every particle would have started oscillating with the same amplitude A. But since each of these particles have their own amplitude depending on their position from the origin, we know that they do not transfer energy. Such waves are what you call as stationary waves or standing waves. Now, we will next go on to discuss standing waves and resonance. You would have noticed that suppose you take a stretched string like a guitar string, okay, and you know that the guitar string is fixed at both ends, and you pluck the string and you let a wave travel in one direction. It travels, let's say it travels along the positive x-axis, goes to that fixed end and then gets reflected back. So on the same guitar string, you have waves traveling along towards the right, the positive x-axis, or towards right and towards left, because you know that the string is fixed at one end, both ends actually. So when it reaches a fixed end, it gets reflected back. So on the same string, you will have right going and left going waves which overlap each other, and because of superposition principle, they produce this kind of interference produces standing waves or stationary waves like we discussed now, because we have two waves traveling in opposite directions on the same string. Now at certain frequencies called as the resonant frequencies, these waves set up stationary waves or standing waves with nodes and antinodes, and at all other frequencies we will have oscillations, small oscillations of the string. So here, suppose we take, let's say this is the string, this is position x equal to 0, this is position x equal to L, because this string, if it's the guitar string, a stretched string, is of length L, and so if this is 0, this will be x equal to L. Now if you pluck the string and set up stationary waves, the simplest mode of vibration will look like this, because at both the fixed ends you can have only nodes, because the particles at that point are fixed there and therefore they cannot move and they are stationary, and these two positions will be positions of nodes, but you will have one antinode, and this is the simplest mode of vibration. You can set it into different mode of vibration, like for example, you can have something like this. Here we have 1, 2, 3 and 3 nodes and 2 antinodes here. So you can set it up into different modes of vibration. Now if I take this case, here we know it is a node, and just now we saw that the node condition is n lambda by 2, integral multiples of lambda by 2. So if I'm talking about x here, this is L equal to n lambda by 2, or lambda is equal to 2L by n. You know that the frequency is given by V by lambda, or frequency is here V by, I'm substituting for this, into n by 2L, or we may write frequency is n times V by 2L. So that means you can produce different frequencies in the same string by setting it up into different modes of vibration. For example, in the fundamental mode, like here, you have 1, where the frequency, the first fundamental mode is 1 V by 2L. If you put it in the two modes of vibration, you can have nu2 equal to 2 into V by 2L, that is V by L. If you put it into the next mode of vibration, 3 modes, then this will be 3V by 2L. And you see, you can put your string, the guitar string or the veena, any stretched string on the same string, you can produce sounds of different frequencies by simply putting it into different modes of vibration. And in the beginning of the chapter, if you remember, we already did V is equal to root of T by mu. Remember? So this is the tension on that string, and this is the mass per unit length, mass per unit length. That is, I told you, different thickness of the string. So this V here depends on the tension and the mass per unit length. Also, the vibrating length of that string will cause the frequencies to be different, and you can produce sounds of different frequencies by simply putting it into different modes of vibration. We will continue in the next session, and thank you.